Thank you, guys. Thank you for coming back from lunch. So, as you can see, the title has changed a little bit. And it's going to be the analysis of Jupiter's deep jets using Juno gravity and the upcoming time-varying magnetic field measurements. It's a continuation of the talk that you saw this morning by Yochai Kaspi. And this is part of my graduate work, which I'm currently at the Weizmann Institute. And I did this work with Eli Galanti, Yochai Kaspi, and HAO. So let me start with a quick motivation. As you can see, this is Jupiter jets, as you're probably familiar with the surface winds. And here we have the very recent published radial component of the magnetic field. And what we're going to try to do today is to try to incorporate magnetic field effects on the flow to try to better constrain the subcloud vertical flow profile. So another important motivation, clearly, is all of the Juno gravity measurement that's been recently published in one of the Nature issues. And we had a few nice papers here, one by ES et al. That revealed the north-south asymmetry arising from atmospheric flows in Jupiter. Yochai, you saw this morning, showed that the atmospheric jets extend to about 3,000 kilometers. And Guillaume showed that below the depth of 3,000 kilometers, Jupiter is rotating like a solid body. But even now, with this all new analysis, the internal structure is still not fully known. And we're going to try to add new constraints to might better solve the flow structure. Now, another important motivation is the recent published analysis of Jupiter's magnetic field. It's been published also this year by Connerly. And here you can see the radial component of Jupiter's magnetic field. You can see a strong dipole, as you all probably know. We can see the blue spot. This is the magnetic field at about 0.85 of the radius of Jupiter. And those observations was collected during Juno's first 8 out of the 9 perijobs. And by the year of 2020, approximately, hopefully before that, we would have the next set of measurements. And this remarkable map of the magnetic field gave us the idea to try to use the changes in the magnetic field, the magnetic secular variation, to try to constrain the flow profile. Now, the current best solution for the flow profile, you saw it this morning, so I'm going to go over this really fast. This is the decay profile of the surface winds. We have also latitude dependency, and this is the match between the measurements and the solution of this decay profile. This was done using the odd gravity harmonics, has been measured from the Juno spacecraft, while assuming thermal wind balance. Now, we, as I explained before, are going to try to use magnetic field constraints to better understand, especially what's going on here in the lower part of the flow, and I will explain soon how. Okay, now the electrical conductivity in Jupiter has been published a few times in the past, and I'm going to show here 2 main estimations for that. We have on the plot a few more. So one is by French et al., which are the 3 red dots. They had a really kind of a bad resolution for the upper part, the semi-conductive region, which is interested for us. They did it using ab initio simulation, and they plotted these 3 dots. This is linear scale, and this is logarithmic scale of the same electrical conductivity. We also have the Liu profile from 2008. This is the pink line. This is interpolation of that. You can see it also here in the logarithmic scale. And they did it using shockwave experiments been done by Nellis in the 90s. Now, the best profile that Yochai showed you this morning extend to about 10% of the surface strength at 4,000 kilometers, which is about 0.945 of the radius of Jupiter. This is this red line. And you can see that neither one of the electrical conductivity profiles that's been published are fitting to the fact that it's going to be that the flow is going to penetrate to areas of relatively high electrical conductivity. Obviously, it depends what you call high, but for the semiconductive region, and it might be high enough to cause flow magnetic field interaction. Now, we also know that the flow already is very low in this region. It's 10% of the surface strength, meaning the highest possible flow is about 14 meters per second. But these velocities might be high enough to cause this interaction between the flow and the magnetic field. Now, we're going to present two dominant regimes for this project. We have the higher regime from Jupiter's surface to the transition depth, as we define here as RT. And this region is going to be a region of practically zero electrical conductivity. And we think that's what's going to dominate the interaction here is the interaction between the flow and the gravity field through thermal wind balance. And the lower part, below the transition depth, we're going to have interaction between the flow and the magnetic field that might be dominant enough to cause some changes in the magnetic field. This is a sketch of Jupiter's surface winds. The red to white is a scheme for the decay of the winds. Now, we're trying to answer a few questions here. For example, where is this transition depth? This is very not well defined. And what kind of magnetic behavior can we even measure? So a previous study published in 2017 by Galanti et al. Used a similar approach, constraining the upper part of the flow using thermal wind balance, and the lower part of the flow using the mean field electrodynamic balance. Now, they assumed a constant transition depth of 0.972 of the radius of Jupiter, and then constrained the flow using these two parts. This is the main equation that they solved for the bottom part by Tassoul and Stevenson from 2017. I'm not really going to go over this. If you want, I would be more than happy to talk about it later. But the general idea was to separate the anomalous field, the magnetic field of Jupiter, to background field, and to anomalous field, which is the A and the B components here. Now, the anomalous field might be caused by interaction between the flow and the magnetic field. This is the solution that they suggested in their profile. They published it when we still had non-measurements for neither the gravity or the magnetic field from Juno. So they simulate the profile. This is the black line that you see here. And they solve it through thermal wind balance, which is the blue line, and through mean magnetic field balance, which is the red line. And finally, they suggested the combined method, which is the dashed blue for the simulation, which is the red. Now, unfortunately, it appears that the magnetic field of Juno, as we saw before, is way too complicated to be able to decompose it correctly into background and anomalous magnetic fields. So what we're going to try to do is to use a similar approach of the two regions, combining the thermal wind balance with the magnetic secular variation. So the basic idea, as I explained, we're going to use the gravity field constraint for the upper part of the flow, where we have fluid that's completely non-conductive. And we're going to use time-dependent magnetic field constraint to constrain the bottom part of the flow and the transition depth between the regions. And we're going to hope to be able to use both fields to understand the flow structure below the cloud level. We hope to find if the atmospheric wind does participate in MHD processes. And we hope to be able to combine two independent measurements from Juno, which is actually way more than two measurements, because we have 4 measurements for the odd gravity harmonics and a complete field of measurements for the magnetic field. So the gravity field constraint you saw this morning, I'm just going to go over this really quickly. This is the thermal wind balance. We're going to assume here only perturbation, only the anomalous density field. And we're going to solve it through the odd gravity harmonics, as you saw this morning by Ohai. And this is the connection. If we integrate the anomalous density field, we can present the gravity field through the odd gravity harmonics. And you already know that Juno was able to measure them, which was a surprise by itself. For the dependent time magnetic field, we're going to solve the induction equation. We're going to decompose the field into poloidal and toroidal direction. You can see it here, the G and the H. And then we're going to use the Chebyshev polynomials for the radial direction and the spherical harmonics for the horizontal direction. And we're going to solve the equation for the potential, for the magnetic potential, poloidal and toroidal field, which I'm not showing here. This is the equation that we're solving here. Now, the simulation and measurements for this project. So we have, Juno already actually measured the odd gravity harmonics. So we have from Juno the odd gravity harmonics, but we don't yet have the time varying magnetic field. We only have the magnetic field as averaged of the first year of Juno orbit. We're going to have the next set only in about a year, hopefully. So we had to simulate that. We chose a decay profile that is consistent with the gravity measurement, and we generated from it, through the induction model, the changes in the magnetic field with time. We also, since we generated a decay profile of the wind, we also have the odd gravity harmonics that came with that. And we chose to use an electrical conductivity profile very similar to the one published by Liu in 2008. And we chose it, I remind you, this is the weaker one that we saw in the figure from the beginning. And we chose to use this one to allow as strong as possible winds in the bottom part. This is just a simulation and just an idea, but we hope it will give us an intuition for what's going to go on. So the setup for our model is such. We have from Juno the odd gravity harmonics. We don't have the magnetic field changes with time, so we simulate them. And we're going to use those two measurements to try to constrain our model compared to the Juno measurements and the simulated measurements. And we're going to make sure that we were able to reproduce both fields. Now, just as a sanity check, we're also going to do it only compared to the simulation. We're going to take the odd gravity harmonics from the simulation and check here as well that we were able to fit both fields. We're going to do it because we hope to get a better solution here, because these two fields are actually related to each other. They were generated from the same decay profile, so we hope to get a better solution here. So this, you can see here in linear and logarithmic scale, the decay profile and the electrical conductivity. I'm going to go over this. So in black, we have Yochai's profile. In blue, we have the simulation profile that we chose for this project. You can see it's very similar to the Caspi profile above 0.97, which I remind you, above this, the conductivity is approximately 0. So it's very similar to it above. And below that, it's similar in trend, but weaker in strength, because we took Yochai's profile and tried to put it in the induction code and see what will be the changes in the magnetic field. And we got two strong changes in the magnetic field. We got non-physical changes. So we had to simulate a new profile. We also see here the electrical conductivity that we're using in dashed red compared to the Liu profile in pink. It's changed. It's pretty different from it above 0.972, but again, this is the region where the electrical conductivity is approximately 0 in both profiles, and very similar to it in the bottom part of our model. Now, those are the results for the changes in the magnetic field from the simulation profile. So here we have the Juno reference model from the first 9 peri-jobs, has been published by Connerny. We have here latitude and longitude, and we have here units of nanotesla in colors. We can see the strong dipole and the blue dot. Here we see the simulation result for the changes in this magnetic field with time. Gray contours is exactly the same as this figure. And here in colors, we can see what changes we are aiming to have from this profile after 1 year. Okay? So we ran our model forward for 1 year, and those are the changes that we got. Now, those changes are make sense in size, kind of. We hope so. This is, again, nanotesla, and you can see it's approximately 1 order of magnitude smaller. Now, here we have the velocity profile in meters per second on the normalized radius in the boundaries of the induction model between 0.93 and 0.97 of the radius of Jupiter. And we can see here it projected down on cylindrical coordinates. And we can see the strong jet here is the one that's actually causing these strong changes in the magnetic field, because it reaches to areas of very high electrical conductivity. So this jet, you don't see it, but on the surface it extends to about 22 degrees north, and it causes the strong changes in the magnetic field at about 10 degrees north. Now, we're going to define here an optimization technique using both fields, the gravity field and the magnetic field. We're going to constrain the upper part using the odd gravity harmonics that's been measured from Juno. And we're going to use for the bottom part, the magnetic secular variation and the simulated changes that I showed you before, that I created, to constrain the bottom part and the transition depth. So the combined optimization, I'm going to go over this pretty fast. So for the bottom part, we chose to fit a simple exponential decay. So this is the surface wind, and we project it down through this Q function, which is defined as a simple exponential decay between the boundaries of the induction code. And we have two parameters to optimize: the strength of the flow at the upper boundary of the induction code and the rate of the decay. Now we're going to use a cost function to define the best solution. To find it, this is the cost function. We're going to go to order and degree 10 for the induction model, as been done in Connerny's paper. And we're going to fit both the toroidal changes in the magnetic field and the poloidal as well. For the upper part of the flow, we're going to use the thermal wind approach. And we're going to fit the 4 odd gravity harmonics in this way. And it's going to be a bit more complicated here. We're going to optimize each single grid point of the model with the limitations of continuous function, negative derivative, meaning it has to decay at all depths. We're going to fit to 1 at the surface, like the surface winds. And we're going to fit to the induction code at the transition depth that we're also going to optimize. So this is what we got. This is the results for the bottom part of the flow, the changes in the magnetic field with time. We can see here the cost map depend on the 2 parameters that we try to optimize, the U and the H. We can see a strong near-linear trend here. This is a logarithmic scale. And we have here in red the best solution that we got for the flow profile. And in pink, all of the first order of magnitude from the best solution. Now, since we did not use the well enough resolution, we decide to average all of the first order of magnitude of the solution, meaning all the dots that you see here. We average them, and we use that as the solution for the bottom part. This is the green line that you see here. In dashed black is the simulation profile below, only in the regions of the induction code, because it's the only areas where it actually matters. We also have the error bar for the solution. And it's easy to see that below the depth of 3,000 kilometers, our solution converges with the simulation, meaning above that, the induction code is non-sensitive at all. Now, combining with the gravity measurements, we got this red line for the best solution profile. We chose the transition depth to be at 0.95 of the radius of Jupiter, which is about 3,500 kilometers. We chose this depth. We were aiming to choose the deepest possible transition depth that we could without harming the magnetic field changes with time result. So we got this point, who still resulted as very good changes in the magnetic field. I will show you this in a second. And we were still able to fit the gravity measurements. We also, as a sanity check, as I explained in the beginning, compared our model only to the simulation. We compared it to the odd gravity harmonics that's been generated by the simulated profile as well. So here you see in dashed black the simulation, and in full black the model solution when we try to fit the simulation. Now those 2 profiles were generated using completely different decay functions. The dashed black, was created using a very specified decay function that we chose the parameters for. And the full black, which is the simulation, the model result compared to the simulation, was found by fitting every single grid point in the upper part. Now, it's easy to see that we got a pretty good match. Now, summary for our model compared to the odd gravity harmonics. Here we see the measured 4 odd gravity harmonics from the Juno spacecraft and its error bar. We can see the Caspi result for those 4 measurements. And we can also see our new model, the red line that I showed you in the previous figure, compared to these 4 measurements. Now, as I explained before, we also did a sanity check to make sure our model optimization is working fine. And this is the simulation odd 4 numbers. And this is the model check for that. You can see that the numbers are very similar to each other. So even though we did not have the magnetic field changes with time, we were still able to fit the 4 odd gravity harmonics while considering MHD effects on the flow. Now, this is just a summary for the results that we got. So here we have the simulation result for the changes in the radial component of the magnetic field. Here we have the model results for these changes. You can see that they're very similar to each other. On the right side, we have the gravity anomaly in red as being observed by the Juno spacecraft, and in blue as our model resulted. Again, you can see they're pretty similar to each other. Now, just to make sure that we were able to fit all, I don't have time, never mind. Just to make sure, yeah. So just to make sure we were able to fit all what we wanted to do. So again, from the Juno, we had the odd gravity harmonics. We did not have the changes in the magnetic field with time. So we simulate them, and we wanted to make sure that our model can fit both the simulation changes in the magnetic field and the odd gravity harmonics, and we were able to fit both. Also, in the sanity check, we did it just compared to the simulation, and we got better values, as was expected. Now, just to conclude, the new combined method that we suggest here offers the use of two independent measurements from the Juno spacecraft to try to better solve Jupiter's internal flow structure. We find that the suggested profile by Yochai is too strong in the lower part of the flow, and that we must add further constraint if we want to really understand it correctly. And we were able to find a single decay profile that fit both of the gravity measurement and the simulated magnetic measurements through optimization technique. And finally, once the new magnetic measurements will be available, we could re-optimize our solution to try to resolve the flow structure even better. I'd like to thank you guys for attention, and if you have some questions, I'd be happy to answer them.
Sorry, we have a certain amount of confusion on this row, especially me. Can you tell us, I can't quite understand, what is the simulation from which you're getting dBr by dt?
So I simulated the decay profile of the wind. The decay profile.
You're just doing a decay problem?
Yeah, I showed it also. Yeah, it's a bit of a confusing process. So here, this is what I explained in the beginning. The black line is the Caspi profile for the decay of the surface winds, and the blue line is the simulation decay profile. We chose a different decay profile that will result reasonable changes in the magnetic field with time, because the black line resulted the changes in the magnetic field that were a few orders of magnitude larger than the ones we just measured. So obviously, it's not good enough.
So you're not assuming any kind of dynamo or anything?
No, we're completely neglecting all dynamo effects.
Thank you.
For the geodynamo, there is an established method called frozen flux approximation by Roberts and Scott, where people take the time derivative of BR and try to infer the tangential velocity with some regularization and so on. Did you check this simple method? If you have ddt of BR, simply to try to formally get out the tangential velocity in the same sense as it is done for the Earth?
Well, I'm actually not familiar with the study that you just talked about.
It's much more sophisticated, I see, but maybe this would be the first thing which would come
I don't know about it, but I would be happy to hear a bit more later. Sorry.
A very interesting talk. I was just wondering, have you or has anyone searched for like a steady state solution? A solution which would match all your conditions by which the magnetic field is stationary. You don't have data on dB by dt anyway, so could you not look for a steady state solution first? Is that impossible?
Do you want to answer, or do you want me to answer?
Yeah, I can say a few words to both Frank's question. The frozen flux condition actually does not apply in this range because we're actually in the semiconducting region. So if you actually plug in the numbers, the magnetic Reynolds number is actually order 1 or smaller. So you do expect like slippage between the flow and the field. So you do need to solve the induction equation. And on the whether you can find a steady state solution, I think if you assume the flows are zonal flow, axisymmetric flows, but the magnetic field are non-axisymmetric, you actually cannot find a steady state solution.
Thanks.
It's more like a magnetoconvection here. Like you assume there's a dipolar field from below, then you try to having the flows in the semiconducting region to modify the dynamo-generated magnetic field. No, I'm not saying that. Yes. Okay. It could be. Yes. Yes.
All right. Let's thank Karen. Next speaker set up here.
This is the wrong donut.
Yeah.
It wasn't the other one. Ah, yeah.
This one here, maybe.
It's loose. Okay, this one. Ta-da! Reset weight.
Well, that happens. Do you want to put this on?
Perfect. Yeah.
You're muted right now, so I'll wait until
Okay. Good. Now you're live. Thank you.
and I will give you 25 minutes of time. So I'll give you a 10-minute, 5-minute warning.
Good.
That's what
Thank you.
All right. Our next speaker is Hubert Klahr from Max Planck. He'll be talking to us about accretion disks and stratified disks.
Thank you very much, and thanks for having me again here in Boulder. It's always a pleasure to come visiting in this beautiful city and to speak not to the usual astronomers crowd which want to observe disks, but people who really understand what goes on hydrodynamically wise in such disks. So I just want to show you what progress we did over the last 2 years. I think 2 years ago I represented some results, so I will continue in the pace today. Ah, yeah. Pushing strong, then you get light. Oh, that's cool. So already on the title slide, you see some of the things which we are doing. So, oh, it's cutting off. No, it's okay. So we are doing hydro simulations of disks, and the application is pretty much what Eberhard gave yesterday. You quite some introduction to the planet formation process, so that we want to concentrate particles in flow structures. That's why I say we are talking about structure formation in disks, and then how from these concentrated particles in the end planets can form. So first I have to thank to my group in Heidelberg, so taken a picture earlier this year when we still had snow there, but now we also have climate change in Germany, so I think this will be a rare picture in the future. So a lot of my research is funded here through German Science Foundation, which is really generous right now. So if you have an application and it says planet somewhere, or live, or exo stuff, and then you have a very good chance of getting funded. So it's really great. So if you struggle here, just come to Germany. So the outline of my talk is roughly as follows. I will give only a very brief introduction on planet formation, and then really dive into the hydro instabilities, and especially the most important thing today is the last row here, really talking about where in such a disk might actually be the conditions for instability. Because I learned recently from some applications for money I did, for research money, that there is still a vague idea about entropy and temperature structure of those disks. And this is something I really want to preach for, so to look deeper into what are actually the conditions to have instabilities. So planet formation takes place in a disk because all the planets are moving in a disk. But it would be nice if we could directly observe the planet formation process, but actually, even if you look for regions where we believe that planets are forming right now, the resolution is pretty bad. And so we zoom here, for instance, into the Orion Nebula, where we know that new stars are being born. And if we zoom in, eventually you see something black in here, And this is now such a protoplanetary disk, a dust and gas disk around a young star. And we believe now that maybe there are planets forming in there, but we don't see it. And what we also don't see is what is the hydrodynamical state of such a disk. Are here magnetic fields in action or not? Is it turbulent? Is it more laminar? It's really difficult to say. So the disk is so dark because there are many of these tiny dust grains embedded in here, which then later have to coagulate and then form the planets in the end. So an artist impression of such a disk might be looking like this. So it's a thick disk, very pretty thick. And the thickness of this disk is basically already an indication that such a disk must be turbulent. So, and that there must be gas in it, that it must be at least a little bit turbulent, because if there wouldn't be gas or if there wouldn't be turbulence, then all the dust grains eventually would sediment to the midplane, and then the system would basically look like Saturn's rings and not such a puffed up disk. So I believe that such a cloud, if we would be able to move really close to that, would be looking like a gigantic sandstorm in the desert. And in the sandstorm, this is now the problem, no planets are forming. So in the sandstorm, just the opposite happens. So sand grains hit each other and grind down to smaller and smaller stuff, and it does not grow. So the remedy for this is basically that then dust has somehow locally to be concentrated in these things. So, but maybe it's not dust. Maybe it's more like ice grains. Maybe ice grains are sticking better to each other. So Doug Lynn and Ed Thomas and myself studied this. We extra went to some snow site, but we also could not find any planet formation there. The problem is in the nebula the same, so snow is eventually falling to the ground, and falling to the ground means in the disk basically that all the snow eventually falls beyond the ice line, is melting away, and then again no planets can form. But this was all done on Earth, so as a student then I was courageous and then just checking whether in zero gravity things might be different. We did some experiments here on a parabolic flight campaign. But you see, the experiment was so successful that we had fun. But again, so also in zero gravity, planets do not form, and therefore I thought, let's do theory. So theory is then maybe giving us better answers than experiments in airplanes. Even this is a lot of fun. So one possible driver of turbulence in disks, and a very solid one, and it works perfectly under the right ionization conditions, is here Magneto Rotational Instabilities. So like here in this simulation that Mario Flock has been doing, a global simulation, and you see here all these wonderful velocity fluctuations. But this is now really truly turbulent, which is forming in there, so that you really have vanishing correlations over time, so that there's a finite correlation time and that the system is not forming any coherent structures. But actually sometimes this was observed even in ideal MRI simulations, like here this meanwhile, what I would say almost early work by Sebastian Froment and Richard Nelson, who found indeed in an ideal MHD simulation long-lived perturbations in the vorticity, so a vortex was forming here. And in this vortex, they could find that particles were getting concentrated. So it was actually the other way around. So they first saw that particles got concentrated when they threw them in, and then wondered why might this be happening, and only then checked for vortices. Because generally it was believed, and still it's difficult to understand, why in an ideal MRI simulation, which is so turbulent, a long-lived coherent structure actually should form. So as I said, this was an ideal MHD simulation at very high, at perfect ionization for all the MRI processes. But meanwhile, we think that the disk has various regions of different ionization levels, and we will hear more about this in other talks, also in the next talk, I guess, by Jeff Roy. So I just want to hint that there are regions in the disk, maybe outside 0.3 AU, and at various levels, even further out, which are sufficiently magnetically damped or sufficiently decoupled from magnetic fields that there's at least a chance to look for other instabilities. So just to mention this, but there will be the talk by Geoffroy afterwards here. If you include, for instance, the effect of the Hall term, then also very interesting structure in such a disk can form. So here you have the ring-like configuration of magnetic fields, and here even a vortex was forming. But I want to hint more now on these red and blue things here, which I would say are now zonal flows and vortices, which may have formed just from hydrodynamic instabilities. And the hydro instabilities, which are currently widely discussed, would here be then 3 of them. I want to mention 2 more in detail, and one I refer then to Phil Marcus later. So 3 instabilities: the vertical shear instability, then all these radial convective instabilities, which I then combine in here, convective overstability and subcritical baroclinic instabilities, and then the vortices. And I choose here to call them 3 musketeers because these instabilities all have their own qualities and also are working for different parameter regimes. So they could really help each other, and you might have, well, one disk which has instabilities of one of those things at various locations, and sometimes they overlap, so they work together, so they are friendly to each other. So the stability of rotating gas systems is given here by the Solberg-Hoiland criteria, which are here. So this dJ by dr, this is the angular momentum profile of the disk, and this is here the entropy gradient. And I have been just rewriting this slightly here because this is then the terminology which we are always using. So the radial gradient of the specific angular momentum is now the epicyclic frequency squared, and r squared, this is the radial buoyancy, the Prundt-Weisseler frequency. And in order to have stability, then this term here has to be positive. And Kr square in a Keplerian disk is a very large number, so this is the stabilizing agent. And even if you have a radial entropy gradient which would be driving convection, typically Nr square is much smaller than Kr square, and therefore most of the time this is stable. So from the second equation, you can basically get the fundamental principle of the vertical shear instability. Here you see that basically whenever you have vertical shear, because kz square you get when there is vertical velocity differences in the disk, this is always a positive number, so minus kz square always wants to be unstable. So if you have a system with vertical shear, it wants to drive an instability. But there again is a stabilizing agent, and this time it's the vertical buoyancy which you have in here, so nz square. So, and this number, and kr square is pretty large, and this would be the vertical scale height, the radial scale height, radial buoyancy. So this term is usually dominating the system, again preventing any vertical shear instabilities. And the solution for this, as we will see later, is that now thermal diffusion, thermal conductivity, heating and cooling can destabilize the systems. In the upper case, it leads now then to an oscillation at this frequency, but which is then growing over time. And in the second equation, if you have very efficient thermal relaxation, then the action here of the buoyancy in the vertical direction is getting diminished. And then, for instance, if then nz, also possible in a vertically adiabatic stratified disk, would be 0, then you see then the entire term disappears, and you're then left here with the unstable part here, the kz square, the vertical epicyclic frequency. So a temperature gradient in a disk makes the disk baroclinic. This means that then suddenly lines of constant pressure and constant entropy are no longer aligned to each other, or density and temperature are misaligned, and this can then lead to a thermal wind in such a disk. And the thermal wind equation for the disk looks like this. You have here the Keplerian frequency, then h over r is the thickness of the disk, a measure of the temperature, and in the last term you have here then this z square over h square. It gives you a parabolic flow profile in the vertical direction. So, so we then start right away here with the Bold-Reich-Schubert-Fricke instabilities, or also known as vertical shear instability. It was Erpen and Brandenburg did work on this on theoretical measures, but then it was later Nelson, Kressler, and O'Murhan who were so lucky to find this really in a numerical simulation. So it was then discovered because finally resolution was good enough in order to have this as a parasite in MHD simulations occurring, and then people started to look into what was actually going on in there. The principle is that now the omega, the rotation frequency, is a function of height. It's a parabola here. And if you then calculate for this parabola the specific angular momentum profile, it's bent outward. And then you can also put in the kinetic energy, omega square r square. It's bent inward again, and then if you just look at the gradients, which I did here, then you see that angular momentum is increasing outward and kinetic energy is increasing inward, so in the opposite direction. And if you now have here a gas parcel sitting on such a line of constant specific angular momentum, then it can move upward and get into regions and brings with it an excess of kinetic energy. And this is basically then the mechanism driving this instability. So, but in order to move up there, you have to move very strictly upwards so that the radial wave number is much larger than the vertical wave number in order to be on this line of constant specific angular momentum, and buoyancy must not stop you, and therefore there's a cooling condition here so that the Brunt-Weisseler frequency, so basically this is now again the epicyclic frequency proportional divided here by the Brunt-Weisseler frequency in the vertical direction, gives you a cooling time criterion, how fast you have to cool in order to have modes moving vertically up and down in a stratified medium. Of course, the other possibility is that your disk is vertically stratified adiabatic, and then there's no strong cooling criterion given for this. Good. So if you are doing such simulations now, global simulations of vertical shear instability, and this is work by my student Natasha Manger, she was studying the effect of doing more and more global simulations. So this was only 45 degrees, 90 degrees, 180, and 360 degrees. And when she was doing this, then she saw that the larger the box was, then the more likely you were forming here, this is vorticity, large, gigantic anticyclonic vortices in such a simulation, which had not been seen before that in vertical shear instability simulations. And here it's not so impressive, and one does not really see that this is a disk, but you can, of course, reproject it here in a spherical on the Cartesian system. You see again the vorticity perturbations in here. These are the density perturbations in the gas, also not too impressive. But if you're now using the pressure density perturbations in here and then calculate what the local dust concentration would be, then you end up here in the upper left corner. And then you see that these are wonderful now locally concentrated dust heaps, and if you then again put in some smearing out mimicking the limited resolution of a telescope, then you get basically an extended vortex, a bean-shaped thing here, which is looking very similar to actually dust things which have been observed with telescopes by our observers. So message is here also vertical shear instability can produce long-lived vortices. We are talking here about hundreds of orbits, which they survived in the disk and started their migrating business, and they are concentrating stuff and could explain observations. So I'm jumping to the second one, also close to my heart, the originally called convective stability, coming from convection studies. So this is now the RZ plane, and we found that there can be now in the RZ plane convection cells, which are initially little epicycles, which are then getting amplified. So again, the stability criterion, again, is here kr squared plus nr squared, which is larger than 0. But you can have now little epicycles, which by thermal relaxation are getting amplified in this fashion here. You see here that the growth rates are proportional to n square divided by omega square, which got lost in this equation somewhere, sorry. And you have here then the cooling time criterion to this. And then you see there's basically an optimum if tau, the cooling time, is on the order of the epicyclic frequency, and then you have the maximum amplification. So, and in this process, basically, heat is being transported in this little epicycle outward, thermal relaxation occurs, and then the material comes in again. So I want to show you a numerical simulation on how these little epicycles grow, and so I don't show you the entire disk, but only a small patch, which will be simulated, and the movie starts now. It's a pretty slow growing instability, so it's good that we can do this in a local simulation, and then over time you see slowly here these structures emerge. I'm plotting here basically the temperature perturbation, and you see start to identify then here these little convection cells. When you see they have a slight temperature excess on the outside and a temperature deficit on the inside, and now they are getting larger and larger. They are starting to merge with each other, and in this process picking up more and more momentum and getting stronger and stronger and even stronger. And because this is a two-dimensional simulation, it will eventually fill the entire box. In 3D, it would look certainly different than you can form other structures, but here it's just going on and stronger. So again, these are then these little epicycles in here. Good. What works in the RZ plane also works in the R phi plane, which was already discussed much earlier than it was called, depending on which, in what paper you took, then it was the global baroclinic instability, baroclinic vortex amplification, and so here the Peterson work, and then Lesueur and Papaloizou, subcritical baroclinic instability, pointing out that you really need a kick to this to have vortices in there. But then again, the things are developing, also then in the R phi plane, also forming vortices in there, sending out density waves, and the entire thing looks basically like this. What is interesting is that both convective overstability and the subcritical baroclinic instability have a very, very similar growth rate behavior. So in both cases, it's proportional to, of course, n squared, the radial buoyancy. Here it's the radial buoyancy, but calculated for the surface density and not for the midplane density, because these are then global modes. You have the same behavior, so that there's an optimum cooling rate. But where for the epicycles, it's the epicyclic frequency. Here, it's now the vortex overturn time, so then aspect ratio and these things in. So this means basically both instabilities share the same physical driver, but are different installments of basically the same process. So now just a quick outlook where these instabilities might be working. This is a paper by my student Thomas Pfeil. It's now on S2PH. It's undergoing some revisions, and we wanted to discuss things with the community, and we already got pretty good feedback, and then we will resubmit it soon to S2PH. So one funny thing about opacities and disks is that they are a strong function of temperature. So then the warmer it becomes, opacities are rising. Then eventually here ice grains disappear, opacities are dropping. Then again, opacities are rising, and then it's dropping again when the dust grains also evaporate. And if you're studying then temperature structure and density structure for models of a constant for a given disk mass and a given accretion rate, then you get these here isocontours of density, of temperature, and this would be then the relaxation times. And now you can calculate what would be the gradients that you get in such a disk. If a disk is completely passive, then this would be the true answer. So that the temperature, even in the midplane, is just -1/2, roughly, so from the irradiation of the star. And you see on the average, this is even true. But locally, due to the opacity variations and internal heating, you can get strong variations in the temperature and in the density gradient, which then results in variations of the entropy gradient, which gives you here two zones where even in the midplane, the entropy gradient switches the sign. Thus, at these places, then conditions for the convective overstability is given. So it's now a question, basically, what happens in a passive disk. Very low alpha values would mean a passive disk. And then you see that even in a passive disk, if you only go up by more than a pressure scale-height, or about 1 pressure scale-height, also the entropy gradient switches sign. So this means even in a passive disk, you will have a convective overstable region up here. So if there is accretion heating down to the midplane, then you get larger and larger, so this elephant shape here. So you have then the trunks of the elephant, which have regions where convective overstability even reaches the midplane. So this is then basically related to what part of the disk are actively heated by accretion and which parts are only passively heated. If you just look for the subcritical baroclinic instability, I said then the entropy gradient is different because now the surface density is the important gradient and then also the vertically integrated entropy. And in that case, surface density is shallower. Then even in a passive disk, you will be basically unstable. Not in a passive disk, no, even in a passive disk at large regions will be unstable. And here you have again the entropy profile, and you see that here between a fraction of an AU out to 70, 80 AU, you will have the conditions to amplify vortices in this. Vertical shear instability can also be studied in that one. You can then check whether the cooling criterion is fulfilled and what the growth rates will be as derived up there. Then you see also that this is for passive disks, you have here out here strong regions for vertical shear instability, and then you also get these additional zones if there's internal heating. There's an interesting region in the inner part here, which we discovered here, and here, of course, cooling times are pretty long. But on the other hand, because of the internal heating, there is basically vertically an adiabatic temperature profile. So, and in that case, the stabilizing action of the vertical frequency disappears. So in combination, the map looks like this. So this is, again, 1 pressure scale height, and these various colors give you now the opportunity for certain instabilities to occur. You can also just ask, what do observers tell us for the subcritical baroclinic instability? So these are the criteria dependent on what adiabatic index your gas has. These are the column density gradients. These are the temperature gradients as determined here for observed disks. And then you find that many of those are in the perfectly unstable regime. So I just finished my talk by pointing out, oh yeah, and I also wanted to say, so there's a review coming out by Vlad Lyra and Orkan Amorhan, nicely discussing properties of these instabilities. And there's also one, a review more on the structure formation and on the importance for planet formation. So Ralf Putritz had been pushing me to do this chapter here for the Handbook of Exoplanets and describing a lot of the things I have been talking about today. And also mentioning 3 other papers from which I'm drawing information today. Thank you very much for your interest.
Hubert, have you checked that numerically the growth rate of the vertical shear instability does scale with HR squared over R squared?
Yeah.
That is confirmed, yeah?
Yeah.
Mm.
Yeah.
Thanks.
We have checked it, whether it's HR squared, I don't remember now, but we measured again the predicted growth rates, right, at various resolutions.
If those large regions of the disk really are that unstable, it suggests that the disk will evolve into a more stable state if it can. Mm-hmm. So power law distributions for these temperatures and densities may be the wrong thing of what actually is trying to model a real disk.
That's what we are aiming for. So that's why we said what happens if there is alpha or let's say energy input provided by those instabilities or other instabilities. What is then the possibility? So basically, once we know, and I hope we work on this, and colleagues are working on this. Once we know how strong, how much alpha will be provided by those hydro instabilities, by non-ideal MHD going on in there, and then also know, which we don't know right now, where the energy is getting deposited. So if all the heat is getting deposited in the upper atmosphere, then we will never heat the midplane. So then we have to redo our work here. So, but if at least some heat gets in the midplane, then this will be beneficial for the instabilities. This was the important thing here. So if there is instability, it's modifying the structure in a way to enhance the instability.
Just on that point, if you just thought only about the radiatively heated zone and the outer part of the disk where viscosity is not important, how many of these instabilities would be happy there?
In which part?
In the radiatively heated part of the disk, the outer part.
The irradiation part. Well, you can see it in here. So this is basically the passive part. You see, as soon as the convective overstability is only possible at a height of 1 pressure scale height, then this is the irradiative part. And then you have basically convective overstability, subcritical baroclinic instability, so you have basically all of them out there. So. And then there are some quieter regions, and then some interesting regions where you have opacity changes in the disks, evaporation fronts, and these parts. Sorry?
I love these elephants.
Yeah.
Any other questions? No, let's thank Hubert.
It worked. Yeah, let's go. Let's go.
Just wanted to make you have your heart race a little.
Yeah, that's okay.
Closing. You're muted right now. So
Okay.
go ahead and get attached. Do you pronounce your first name Joffrey? Joffrey. Okay. Thank you.
All right, our last speaker before the coffee break, Jeffrey Lussier, is going to talk to us about self-organization.
Thank you. First, I would like to thank Araquel for this invitation to come to this very diverse conference with people with very different backgrounds, so I've learned a lot. And here is my little contribution regarding the physics of protoplanetary disks. So the work I'm going to talk about here is mostly the work of William Bethune, who was my PhD student, who is now in DMTP in Cambridge, and Antoine Riel, who is a postdoc now in Grenoble with me. So being French means that I'm obsessed with foods, and this talk won't be any different. So in this talk will be divided into 3 parts. First, I will try to show you a short review of how accretion works in disks, and then I will try to give you some overview of the current observational constraints we have on protoplanetary disks. And finally, I will focus more on the role played by surface magnetic winds. Okay, so first thing first, accretion theory. So we've heard about that already, I think, yesterday. These disks are accreting, protoplanetary disks are accreting, and you have several ways to measure the accretion rate. But typically what's done is to look at the luminosity of accretion stream falling onto the young star. Can you see it? Yeah. So this excess luminosity allows you to derive how much mass is accreted. So that's typically what you find. I'm going to switch. Here is what you find. This is the mass of the central star, and this is the mass accretion rate in solar masses per year. And what you see is that for typically one solar massive star, you get typical accretion rates which are between 10 to minus 8 and 10 to minus 7 solar masses per year. So this is your goal as if you want to compute, to do some accretion theory, this is what you should aim for. And that's actually a lower limit because that's only what's accreted onto the central object. Some matter can be lost on the way, like if you have winds coming from the star-disk interaction region, which we know are happening. You can have winds outside as well. So that's really the lower limit you should reach as a theoretical astrophysicist. Okay, so how do you do that? You do that by writing down the angular momentum conservation equation, which I've done here for you. So a way to do that is to look at all your quantities and you average the velocity and magnetic field and density fields in the azimuthal and in the vertical direction over the typical thickness of the disk, which is h. And the end result is this equation, which is the angular momentum conservation equation, and you have three terms. The first one is how much accretion you have. That's the average mass flux, the radial mass flux. That's related to the radial gradient of this funny correlation tensor, which is often called the turbulent torque, and which will be written later WR phi, which is averaged. And you also have a surface term when you do this integration, which comes from the surface, both surfaces of the disk, which is written here and which I will call later the wind torque. So physically what's happening really is that if I consider one annulus in the disk, in terms of angular momentum budget, this annulus is going to fall down if it loses angular momentum. And the way to do that is either to say that the angular momentum coming radially is lower from the inner side than from the outer side. That's the turbulent torque. Or you can just extract the angular momentum vertically, and that's going to be the wind torque. So historically, people have mainly focused on the turbulent torque. So that's what I'm going to do for the first part of the talk. I'm going to get rid of the wind and only consider radial transport of angular momentum. So as you can see here, what we're talking about here is really, it's just a closure problem. If somehow you manage to describe this correlation in terms of the large-scale quantities, meaning density, magnetic field strength, etc., then you can close the loop and tell how much accretion you have in the system. So that was the initial objective of the alpha disk model, which we've heard about. And the idea of Chakwas and Yaev in 1973 was just to create a dimensionless number out of the radial stress. And this dimensionless number, you choose it to, for the dimensions, you choose the local rotation rate, the local scale height, and the local density. These are the only quantities you can choose, right? So really, I would like to stress here that the alpha disk theory is not quite a viscous disk theory, even though you can see it as a viscous disk theory. But really what's happening here is that it's a way to describe a dimensionless stress in the system, and that's it. So if you want to match the observed accretion rate I was talking about before, you need typically alpha value of the order of 10 to minus 3. So later came, in a very nice day in 1991, the Magneto Rotational Instability, which provided linear instability, provided that you are in the ideal or quasi-ideal regime. And this instability creates turbulence in the system. And now if you measure the stress, it turns out that you find, roughly speaking, the right value. So in 91, everybody was happy, problem was solved. It turns out that life is more complicated, as we've heard from Hubert. And unfortunately, if you want the MRI to be active, you need the gas to be coupled to the magnetic field lines, which implies that you need to have free charge carriers in the gas phase. In protoplanetary disks, this is not such an easy task. Why is that? It's because these disks are quite cold, typically At 1 AU, we are talking about 100K, so it's not quite a plasma. And you have very few ionization sources in the system. So first, you can ionize the disk thanks to heating due to the central star, and that's going to work mainly in the innermost AU. Then you have radiation coming from the central star, especially high energy radiation, EUV and X-rays. And these guys are going to fly above the disk and penetrate only the uppermost layers of the disk. And finally, you have cosmic rays, which are emitted from, we don't really know, but we know they're there. Somehow they exist and they manage to penetrate the outer layers of the disk and ionize material down to the midplane, maybe. So you see that you're left with this wide region where the ionization fraction is small, and by small, I mean really small, typically an ionization fraction of the order of 10 to minus 13 or 14. So that's really small. That means that you can't work in the ideal MHD limit, and that means that you have to take into account what's called non-ideal MHD effects, and you have three of them. First, you have ohmic diffusion, which is due to the collisions between electrons and neutrals. You have ambipolar diffusion, which is due to collisions between ions and neutrals. And finally, the Hall effect, which is not a diffusive process. It's just a drift, but it happens to have several interesting consequences on the structure of this disk. So now, if you want to compute the amplitude of each of these effects, you need to assume something about the disk structure. You need to solve for the chemistry. You need to assume something about the grains. You need to assume something about how much cosmic rays you have. It's a hell of a mess. So really, I'm hiding here a lot of literature. This is, for instance, what you may find using the most refined models available today, which include thermochemistry, ions, cosmic rays, I mean, everything mostly. I'm not saying it's the truth. It's, well, the best models we have for the moment. So what I'm showing here is the distribution of ambipolar diffusion in a disk. This is radius, this is vertical direction, and I'm showing here the log of the Alsacer number of ambipolar diffusion, so you can see that as a sort of effective Reynolds number for ambipolar diffusion. You see that the disk is mostly green, which means that you are in a region where the ambipolar Alsacer number is between 1 and 10, roughly speaking. So it's really diffusive. That means that you are in a region where the MOI is severely damped. And Jake Simon have shown that in such a regime, the typical mass accretion rate you find are of the order or less than 10 to minus 9 solar masses per year. And that's, you know, between 1 AU and 100 AU. So that's called the dead zone. Now, this was pointed out first in 1996 by Charles Gammy, just using ohmic diffusion, and this has been enlarged by Eugene Cheng in 2011 and showing that most of the disk is actually dead. That means that you are in trouble. And that's why people have been looking recently more seriously about hydro instabilities in their systems. So we have a zoo of hydro instabilities. Hubert has been describing some of them. Phil will talk about the zombie vortex instability, I assume. And, well, you have all of these instabilities with their own characteristics, et cetera, et cetera. Bottom line is we don't really know for the moment what's driving accretion from these instabilities. So when you don't know, you turn yourself to observers. Well, you try. It turns out that they have things to say. Here I will only review what we know about the dynamic of dust grains, and Jake will talk about other observations about direct probes of the turbulence based on lines which are associated to the gas itself. So I will just focus here on some of the observational evidence, and Jake will show you tomorrow some other observational evidence. So I'm going to talk about dust settling and how it's linked to turbulence. So the picture is really, really simple. In a disk, you have the gas, which has a finite scale height. and you have dust grains. These dust grains are floating in the disk, and they tend to fall toward the midplane because the gravity projected onto the vertical axis points toward the midplane. So dust naturally tend to settle down toward the midplane in a very thin layer. Now, if the disk is turbulent, that's going to counteract on the dust, and that's going to make your dust layer thicker, okay? So you have a competition between vertical gravity and turbulent steering, as simple as that. So typically, this is described as a function of the Stokes number, defined here. It's the orbital frequency at the radius you're looking at, times the stopping time of your dust grain. So as dust grain gets bigger, the stopping time gets longer, okay? So small Stokes means small particles, small grains. Now you can write a very simple model of what's happening, this competition between gravity and turbulent steering, and what you find is that the ratio of the gas disk thickness to the dust gas thickness, to the dust disk thickness, sorry, goes like 1 plus Stokes over alpha, alpha being the turbulent parameter, to the power 1/2. So if somehow you manage to measure the thickness of the dust layer, you have an indirect probe of what's alpha. As simple as that. So let's do that, right? There is a first way to do that, which is to look at this famous image of the disk of HL tau. Some of you might have seen it. So that's a young protoplanetary disk where we see ring-like structures. So I won't go into the details here to why there are rings in this system. But the important point here is that we are probing the dust, which are typically at a size around 100 microns, typically. Now, you can see that there are rings, and you can see that there's rings, and the gaps are very well defined. They don't really depend on the location, the azimuthal location where you're looking at. So now, if you look at this very simple model, this is a a structured disk, where I have assumed that the dust layer was very thin, and here it's a dust layer which is rather thick. So these are actually torides and not thin annuli. And as you can see, the gap, the aspect ratio of the gap depends on the location, while here the aspect ratio of the gap does not really depend on the location. So by looking at the gap aspect ratio here, you can constrain this ratio, which turns out to be smaller than 0.1, meaning that the dust layer is much thinner than what you would expect if the thing was fully turbulent. So here we are talking about 100 micron size grains, which means Stokes number between 10 to minus 3 and 10 to minus 2. So that means that alpha is smaller than 10 to minus 4. Okay? So you might not believe that. You might say, well, but yes, this is very difficult to measure the gap aspect ratio, and I would agree with you. So let's do another thing. Let's look at a disk seen edge-on. We have some of them. Here is an example. It's a well-known object called HH30. This one is seen by the Hubble Space Telescope. It's seen edge-on, so the disk here, that's in the visible light. The disk is this dark band you see in the middle, so you don't see the central star. The only thing you see is light scattered by the very small grains, less than a micron, which are floating above the disk. So you see scattered light on both sides, and you see a jet, which is in green here. So that's the visible light, and the idea was to probe what was happening for small grains by looking at submillimetric emission due to these grains. And this is what you find. So that's observation done with the ALMA telescope, and there is absolutely no cheating here. The red stuff is showing you the dust distribution, and the gray stuff is showing you the very small grain, micron-sized grains distribution, which is following the gas. It's quite obvious here that millimeter-sized grains are settled, right? So you can measure that, and you find, once more, then the dust thickness is less than 10% of the gas thickness, and that's really an upper limit. So again, the typical alpha parameter is less than 10 to minus 4. So bottom line, on a theoretical point of view, it turns out that the ionization fraction is too small to sustain an efficient MRI turbulence in these systems. From an observational point of view, it turns out that the vertical settling is telling you that turbulence is very weak, and dust grains are typically 100 micron and millimeter size tend to be settled toward the midplane. There are also evidence, as I was saying, from turbulent line broadening that there's the RMS velocity of these disks is very small, much smaller than what you would expect from and what you require from full-blown MRI turbulence or any hyper instabilities. Which leads to the question, but what is creating this accretion? Because we know for sure that the disks are accreting. So here is a plausible scenario, which is based on winds. You remember this term I have neglected in the angular momentum equation. So let's put it back. So first, well, being a theorist, I try to avoid doing experiments in real life because that can turn into a disaster. So I'm just going to show you a movie, and well, if you want to do the experiment, talk about that later. So here's a movie. I'm going to take an aluminum disk. That's going to be my disk. It's conducting, and I have a magnet. I'm going to rotate the disk in this little device. It's a very simple experiment. And you rotate the disk, you take your magnet, you put the magnet near the disk, and the disk stops. As simple as that. Once you have understood that, you have understood how winds are working. Why is that? When you have stuff which are beating around a central object, if you slow it down, the stuff falls. Satellites, for example, when they reach the atmosphere, they fall. So here it's the same thing. By having an external magnetic field, and by plunging my disk in this external magnetic field, I can slow it down and therefore create accretion. So this process turns out to be quite efficient. If you take, again, this angular momentum conservation equation, you look at the turbulent torque, you look at the wind torque, you compute the ratio of the two, and you find that this ratio is proportional to the R/H ratio, which is something which is larger than 10 or 20. So this process is actually very efficient at removing angular momentum. So how do we do that? Well, this is the kind of picture people now have in mind. Typically, we have a dead zone, but you have to remember that you have this upper layer, which is ionized by X-rays and far UVs. So by plunging this very thin layer in a magnetic field, I'm going to create accretion at the surface, not in the midplane, of course. But since this process is very efficient, I'm going to be able, hopefully, to match the observed mass accretion rate. So this is a model which has been looked into by several people, like Xuning Bai and Jake Simon. Well, this is still in its infancy. We don't have any reliable prediction for it. So I'm just going to show you one numerical experiment trying to demonstrate how this thing can work. So here is the setup of this numerical experiment. We have a central star. We have a disk where the ionization fraction is computed on the fly. So we have all the non-ideal effects here. We have poloidal field lines, which are initially straight, threading the disk. And we follow the evolution of the disk. This is the kind of outcome you get first during the first, let's say, few tens of orbit of the evolution of the disk. So I'm showing here the the poloidal field lines. You can see that they are bended outward, so that's the ideal configuration when you want to have a wind. You can see also that you have lost the top-down symmetry, and the reason for that is that currents cannot stay in the midplane because you don't have charge carriers, so the current layer has to move on one side or the other. So this time it chooses up, sometimes it chooses down. You can also see that if you look at the radial velocity, you have this very thin blue region, which is matter falling in. So that's my surface accretion stream, which is lying here. And on the other side, we have this strong red region, which is essentially a wind, which is going outside. So angular momentum is taken from this region and put in this material, which is leaving the disk. Now let's look at the angular momentum conservation equation once more. We have this, again, the turbulent torque, which is here, and the wind torque, which is here, and we can measure each of these terms in this sort of simulation, and that's shown here as a function of time. So the black line is the mass accretion rate, so it's negative, so stuff is accreted inward. The blue line, which is oscillating around 0, is the term associated to the radial transport, so that's turbulence. You see that it's not contributing to the angular mass accretion. And the red stuff is the wind term, and you see that it's around what's measured for the mass accretion rate. So that demonstrates that you can create accretion only through this term, which is driving accretion from the surface terms. If you put numbers, you find that the mass accretion rate is, in this case, equal to 10 to the minus 7 solar masses per year, so it's even above what's been measured on the central star. And you see that also you lose a lot of mass in the wind, which is not necessarily a problem, as we now have observation of quite massive winds in the systems. Next, if you let that thing evolve for some time, you find that instead of being of staying like more or less homogeneous, the system tends to organize into regions where the field is concentrated, surrounded by regions which are essentially field-free. So that's what you can see here. And if I make a cut through the midplane, I can measure the density profile, which is shown here, and the magnetic field profile, which is shown in red. And you can see that the two are anti-correlated. So you have regions where the wind is strong, where there is no much mass density, and you have regions where the field is weak, where most of the mass is accumulated. That's quite interesting if you want to explain some of the structures we see, like this image of HLTO I've shown. Now, I'm not saying this is the final word, but that's quite, let's say, encouraging. So to summarize that, here's a movie, because we need to show movie when we do simulations, right? So here's a movie of here density, magnetic field lines, the magnetization, and the streamlines and temperature. So what you can notice is that you start with a disk which is more or less homogeneous. You see that the field lines are twisted, so that's essentially the breaking of the disk, which is acting on this field line. So you see that this twist here. The magnetization here, you can see that it's blues, meaning that the magnetic field is strong here in the upper layers, and it's red in the midplane. You start to see there's organized features here, and you see the streamlines where you clearly see that you have material which is lifted up from the disk surface and untrained away from the disk itself. Okay, so you can get back to the question of what's happening to dust grains, because remember that I started by saying that dust grains were sedimented toward the midplane. So we've done that by zooming on the disk region, so on this little region here. So that's a zoom on the same thing. These are local simulations so that we can track more precisely dust grains in this sort of system. So that's a gas distribution. You see that you have this high density region, and here a strongly wind emitting region. So this is a gap here. And we have put dust grains in there. And you see that the dust grains are quite settled toward the midplane, as you would expect. And here you see that grains have been cleared up. So if you do now if you try to plot the vertical distribution profile of dust grains, you find that they are quite strongly concentrated here as a function of z in the midplane. And I'm showing, so the red line is the result from their simulations, and the orange line is the ALMA constraint coming from the observation of HLTO. And you see that it's quite a good fit. So we managed to have strong settling and at the same time the right accretion rate. Are these things observable? Well, I don't know, but I would like just to point out that now we have good evidence for winds coming from the outer regions of these objects. These are called molecular flows. Here is an example. That's the same HH30 image, so it's a disk seen edge on. You see the outflow coming only from one side, and you see here what's called the low velocity component, which is quite compatible with the kind of winds you would expect from this sort of model. So I'm not saying this is a proof, but that's indicative that maybe we are on the right track. So, to summarize, first, observations indicate that disks are likely weakly turbulent, and this turbulence is probably not sufficient to explain the accretion rates. The inclusion of all non-ideal MHD effects lead to an extended dead zone, so the MRI cannot really work in this region between 1 AU and 100 AU at least. It's possible in principle to reconcile the low level of turbulence with the high accretion rate by saying that we have wind launched from the upper ionized surfaces. And cherry on the cake, it turns out that these winds do not stay homogeneously distributed, but tends to accumulate poloidal field lines and create radial ring structures. And I thank you for your attention.
So the density is much lower when you're up several scale heights, where you might have these winds.
Yep.
Is the way that you get the sufficient accretion rate just that the velocities are more coherent and much faster? So even though the densities are lower, it's good enough?
Yeah, exactly. So the point is that essentially when you have a wind, you can drive accretion at the sonic speed, which is much, much faster than viscous accretion in standard alpha disk theory. So that's why you can match the accretion rate you would get from a viscous disk.
Jeffrey, I was interested in the ratio of mass loss to accretion rate that you find in your models. There aboard a Unity, observations have often showed that the accretion is 10 times more than the wind mass loss rate. This should be a very efficient mechanism of extracting angular momentum. And in the models and calculations we did many years ago, without indeed the non-ideal MHD, although we did do ambipolar diffusion in one of our models, did find that very favorable ratio of 10 to 1. So what is there in your model that makes it so inefficient in terms of the mass loss?
So the main reason why you can get such a high ratio is that the wind is not only magnetically driven. There is a fraction of driving which is due to thermal heating of the central star. So if you look at the energetical budget of your wind, you see that you have, of course, a contribution coming from the magnetic field, but also a contribution coming from heating due to X-rays and UVs. So that's why these are not called magnetic winds, but magnetothermal winds. It's because you have both contribution. Now, with respect to observations, it is true that if you look at jets, you expect lower ratios. Now, if you take the observation of molecular outflows, they find from the velocity maps and the CO emission lines, they find outflow rate integrated, which are of the order of 10 to minus 7 solar masses per year, which is fairly high. So it's compatible with that, and the reason is technically that you have help coming from thermal heating of the central star.
So this low effective alpha of 10 to the minus 4 has interesting implications for transport of solids in the disk, and that's much less efficient. And so you present a challenge to people trying to explain the origins of things like chondrules and CAIs and the like, and where they formed and where they end up.
Yes, indeed. It's not the only, it's one of the problems, of course. There are many, many things in Desmo, in what we understand of this disk which rely on the alpha disk parameter. CI and chondrules are one of them. It's also all the planet migration theory which has to be revised because it relies on viscosity theory. Type 2 migration relies on viscosity theory. So the answer is we are really at the infancy of this whole business. We don't have any good closure. We only have big simulations. So, it's quite not really easy to figure out a general model from just these things. And now people are starting to look into planet migration rates and the impact on dust grains and chemistry in these objects. So we are at the beginning, I would say. But I agree. A lot of things has to be revised.